So it's been recently brought to my attention that some people don't know how the sub works. So I'm going to give a quick overview here. All right, so let's start with the path of drivers to state. That's just this little bit here. We got the DVL, we got the IMU, we got the depth sensor. And from those, we get linear velocity, absolute orientation, and an absolute Z. Those all get fed into the EKF and turned into odometry data. All right. We can see that also in the magical RQT graph. So we can see Gazebo spits out a bunch of fake sensor data. We got an IMU, we got a DVL, we got a depth sensor. Those feed into the drivers that republish those to match what happens in the subdrivers. And if we follow all those absurd lines, we'll see they feed into the EKF. Now our controller, we can see, is this pose PID. So the way that works, if we jump back here, so this is effectively what the pose PID is. So in our controller matrix launch file, we launch all our control loops. This is just showing one example, the yaw. So we have a yaw PID loop, and we also have a yaw visual servo now for the DICE state machine. This is currently a bang bang, and this is just a PID loop. So basically, the EKF provides, well, it's not direct. The EKF goes into pose PID node, which does point and shoot um, integration. So if we drive forward, then we have more drive accumulated. If we strafe, we have more strafe accumulated. So, if, for example, if we drive forward 2 meters, turn left, drive forward 2 meters, even though we changed 2 on X and 2 on Y, drive is still 4, even though our EKF state shows we're at 2, 2. So this state is actually the drive state, which is coming from pose PID, which is doing point and shoot integration. Now for yaw, it's actually a little simpler because basically what happens is the IMU spits out an absolute orientation, which has an absolute yaw. That gets filtered through the EKF, but pretty much comes out the same. And that state feeds directly into the yaw PID loop. Another thing I should add, magnetometer calibration. So when we set our declination basically in the IMU driver, and that gives us basically a 0-degree reference frame. So when we're in the pool, we set that to 77 degrees, and that means our zero reference is facing out towards the start gate. That way we have a consistent coordinate system for all our priors, for our obstacles. All right, and so then basically we have a set point, we have our state, and that feeds into the yaw mux. And that yaw mux is simply switching between these two control methods, depending on if we want to do visual servoing or if we want to do a control based on um, the EKF and the sensor fusion data. And that goes into the thruster allocation matrix. So all this is it's a matrix that maps basically yaw drive strafe inputs. So that's a 1D array of yaw drive strafe. And we have a 2D matrix of the thruster allocation, which basically is one side is the drive strafe, which type of thing we're doing. The other is which motor. So right motor, left motor, that multiplies through. We get another one-dimensional matrix, which tells us what our motor thrusts are, right? So we're getting control effort out of these. It's muxed into the thruster allocation matrix. What's our control effort on drive? And then that translates into a PWM for the Pololu, which then increases the motor power, motor thrust. And then that feedback loop, right, we move, we get some linear velocity, we know our orientation, that fuses in, we get the new state, and the PID loop keeps us in that state. So now the next interesting one is the yaw visual servo. So the yaw servoing right now, the way it works with the DICE state machine is, well, real quick, where is, just want to show you. So the pose PID, you can see we have all of these, we're feeding state into the PID loops, right? And that's going out to PID Pololu. So the thruster allocation matrix is, where is that node? Well, it may or may not be in here. I'm not seeing it, but you can see all our pit loops: depth, strafe, yaw, drive, the yaw mux. We haven't put muxes on the other ones yet. Then we have our roll and our pitch pits, which we don't usually use. And that goes into PID Pololu with the control effort. Okay, there. So our thruster allocation matrix is in here. And instead of going to the Pololu driver, we're going to the fake Leviathan motor control, which is fitting in the gazebo, telling it what our thruster should be. So that's what it looks like in our QT graph. That's what this here stage is. All right, so now for the visual servoing. So basically, we have the Occam driver generating images, Darknet's making detections. We tap off there into the dice state machine. So the dice state machine can do two things. It can either be searching and going to the prior, in which case it's just using the waypoint navigator, which we'll talk about more in a sec, or it can be setting the desired image position. So generally, we're ramming dice, we're setting this to the center of the image, which in the case of the Occam is 376 pixels. Then we set the object image position, which we are just looking at the X-min and X-max out of the Darknet detection bounding box. We grab the most probable one in case Dice 5 does get hit. It's also possible Dice 5 will have a higher probability in its detection, but haven't tested that thoroughly yet. Hopefully we can train the net to do better. Anyway, so that feeds through to our Bang Bang controller. Right now, it's set up to have a 30 pixel wide window, so it's just going to bounce back and forth on that dice, and we're going to order the waypoint navigator, which is still running to basically, or no, sorry, yeah, okay, I'm missing a piece here. In this particular state, when we're doing visual servoing, we bypass the waypoint navigator and just send a direct drive command, which basically lets us move forward while pointed at the dice. So we switch this mux, we switch from this control after we've gotten the prior to visual servoing control. So now our yaw control is coming from the visual servoing. Then once we think we are pointed at the dice, we send a depth or a drive command, not this particular one. So basically drive would be here feeding the thruster allocation matrix. We give it a drive a few meters forward, and that hits the dice. So to see that in the RQT graph, that is here. All right, so let's see if we can find that in here. So we got our state machine, and it's sort of encapsulated. All our state machines are encapsulated in this node. You can see we're feeding a set point into the YAW-CV node, which is then muxed in and eventually goes out to our motors. So I'm not sure why that, maybe, probably the state topic was not being published at this point or something, because we don't actually have it going into YAW-CV. But the state machine is going to be tapped into Darknet directly somewhere around here. Oh man, this is just a mess. Somewhere on this thing, Darknet exists. Let's see. Should be connected to the mapper. Oh god. Should be, here it is. Okay, Darknet. There we go. Okay. Darknet feeds directly into the state machine, which then the dice state machine, it's publishing set point and state, which is then letting us point at the dice. It's also directly publishing drive. Yes, we can see it's directly publishing drive in the dice state machine, which lets us control that and bypass the waypoint navigator, which is here. So now let's go a little bit more into the waypoint navigator. So once we have a prior, so we know where we want to go, the state machine tells the waypoint navigator, go here. The waypoint navigator very simply does the reverse of the point and shoot integration, right? So when we are running our EKF, we're trying to figure out what our state is, we're doing point and shoot. Same thing for the waypoint navigator. It has a couple other modes, but the most important one is the point and shoot. It sets our yaw to point at the destination XY, and then sets our sets our drive to the two-dimensional distance between us and that point. And of course, the depth is just published directly. So we point at the XY coordinate we want to go to, we drive that distance, and we set our depth in the waypoint navigator. Right, so that controls us for any kind of world space pose movement we want to do. And how we decide what points we're going to? Well, we have priors, which are from the state machine config, and we have CV. So let's jump back over to our CV. Right, so we have the Occam driver that feeds into Darknet, which puts out detections, which feeds into our localizer. The way our localizer works is we basically, in the detections, we take in the image for classical CV processing as well as the bounding boxes. So if we see we have, say, for example, gate bounding boxes, we send that image to be classically processed plus the gate bounding boxes, in this case just the poles, to a gate analyzer server. Then once that's classically processed the image, in this case finding the 4 points on the gate, running that through the CV function solve PNP, which takes in 4 points and a known set of points in meters of the gate. So basically the same 4 points, their positions in space relative to the center of the object. And that gives us a relative pose. That pose is transformed into the odometry frame and fed into the localizer. So there's also a little bit of filtering in here. Right, so now the localizer knows where in world space the obstacle is. And we send it to the mapper, and the mapper keeps track of that and feeds that information out to whoever needs it. So in this case, the gate state machine uses that to decide where we're going. So first it does a simple search, right? It's just going to the prior. Picks up enough detections that we have a good pose for the gate. It tells the waypoint navigator, hey, don't go to the prior anymore. Go to the gate. And the waypoint navigator gets its set point, and it feeds that through the rest of the system. So now if we look at that in the RQT graph, and start at, where are you? Darknet. Oh man, I just had it. Ah, here we go. Darknet. So you can see Gazebo generates camera images from its 3D engine. Then we have relay nodes, which are republishing to the topic that's on the sub. In this case, the topic is Occam Image 0. Right now, Darknet ROS is only feeding into one of the cameras. Eventually, we plan on doing all the cameras into Darknet ROS. Anyway, so Darknet ROS generates the bounding boxes. That feeds to the localizer client. So I believe this graph only has pub sub architectures, so we can't see that there's in fact a gate server probably sitting over here somewhere. Gate localizer, right? So that's, I believe, our gate server. So we don't see a line connecting those because it's not pub sub. It is instead server client model. So localizer sends over gate images, gate pole images with the bounding boxes. It gets back a world space pose and it sends that to the mapper. The mapper is kind of just a glorified pose talker. It sends out the poses repeatedly, the last good pose. I used to have some filtering. I don't think it does anymore. I have to double check. So the mapper gives the state of the state machine. The state machine's in gate mode, and it says, okay, I got this new place I want to go. It tells the waypoint navigator, and the waypoint navigator then feeds into all the control, and then the control controls the thrusters, and the feedback from the EKF comes in through the the sensors, the drivers, to see how much we've moved, and then eventually that feeds back into the state of the PID loops, and that is our control. So that's pretty much a breakdown of how the sub currently works. Hopefully that gives you a good idea of how to run it. That's how all the pieces are connected.